Hey Calculus class! Tonight we're going to talk about topic 59, sequences. So we're going to start off with the definition. And a sequence is an ordered set of real numbers, a sub 1, a sub 2, etc. to a sub n, and then a sub n plus 1, and so on. That for every positive integer n, there is a corresponding number a sub n. Therefore, a sequence can be defined as a function whose domain is the set of positive integers. The number a sub 1 is called the first term, a sub 2 is the second term, and in general, the a sub n is the nth term. We will deal exclusively with infinite sequences, and so each term a sub n will have a successor a sub n plus 1, and then that one will have a successor, etc., for an infinite number of terms. And instead of using the function notation f of n, we usually write a sub n, which can be denoted with the little squiggly brackets a sub n, or the squiggly brackets a sub n, where n starts at 1 to infinity. So there are different types of sequences. The first type is what we call an explicit sequence. So a sequence is defined explicitly if there is a formula that allows you to find individual terms independently. So for example, if we are given this general formula for a sub n, where a sub n equals 1 over n squared plus 1, I can find the a sub 12, which means I'm going to find the 12th term by plugging in 12 wherever there is an n. So when I do that, and I simplify, I get that the 12th term is 1 over 145. And the second type is a sequence is defined recursively if there is a formula that relates a sub n to a previous term. So for example, if we want to find b sub 3, if b sub 1 equals 4, and b sub n equals b sub n minus 1 plus 2, for all n greater than or equal to 2. So with a recursive sequence, what this means is that I'm going to look at the previous term to get the next term. So in this sequence, we are given the first term, which is 4, and to get the next term, according to this, I have to add 2 to the previous term to get the next term. So that means I'm going to add 2 to b sub 1, so 4 plus 2 gives me 6. And then to get the next term, I'm going to add 2 to 6, which will give me 8, which is b sub 3. And basically you have to keep doing this until you get to the term that you need. The next type is what we call an arithmetic sequence, and this has a common difference between terms. So for example, if we have the sequence -5, -2, 1, 4, 7, and so on, we will find that between each term there's a difference of 3. That's the common difference. Now, arithmetic sequences can be defined recursively. So that means that I can take the previous term and add the common difference. So in our example here, that means my definition for this sequence recursively would mean to take the previous term and add 3, where the first term is equal to -5. And if I do this, -5 plus 3 does give me -2, which is the next term, and so on. Now you can also define it explicitly. And when you define an arithmetic sequence explicitly, it represents the following equation. A sub n equals a sub 1 plus the common difference d times n minus 1. So when I do this, I would get a sub n will equal -5, my starting value, plus my common difference, 3 times n minus 1. And if I simplified that, that means I would get 3n minus 8. And if you notice, this arithmetic sequence, when written explicitly, resembles linear functions. Well, it is a linear function, where your common difference represents your rate or your slope. Now, the fourth type of sequence is a geometric sequence, and this has what we call a common ratio between the terms. So, for example, if we look at the sequence 1, -2, 4, -8, 16, you'll notice that they're not increasing by the same amount each time, but instead, if I was to multiply or divide, I would get what's called the common ratio. And in this case, the common ratio would be -2. So if I did 1 times -2, I would get -2. -2 times -2 gives me 4. 4 times -2 gives me -8, and so on. And these can also be defined recursively, where basically you take your previous term and multiply by the ratio. So in this example, the recursive formula would be that a sub n equals -2 times a sub n minus 1, where a sub 1 equals 1. Now, we could also define it explicitly, and that would be a sub n equals a sub 1 times the ratio to the n minus 1. So in this case, my a sub 1 is 1 times my ratio -2 to the n minus 1. And when I simplify that, I just get -2 times n minus 1. So geometric sequences are exponential functions when written explicitly. So let's look at some examples. So for this first one, list the first 5 terms of the sequence n plus 1 over n factorial. And just in case you have not been exposed to factorials, n factorial is read as n factorial. It is defined recursively as n factorial is equal to n times n minus 1 factorial, or you can think about it as n times n minus 1 times n minus 2 times n minus 3, so on until you get to times 3 times 2 times 1. So if I was to list the first 5 terms of this sequence, that means I'm going to put in 1 for n to be my first term. So when I put 1 in, I'm going to get 1 plus 1, which gives me 2, all over 1 factorial. Well, 1 factorial is just 1 because you can't go backwards from 1. And you keep doing this. You do it with n equals 2, n equals 3, n equals 4, etc. until you get to n equals 5. When you do that, you're going to get the sequence 2, 3 over 2, 4 over 6, 5 over 24, and 6 over 120. Now let's look at how would you find a formula for a general term a sub n for this following sequence. 1 over 2, 2/3, 3 over 4, and 4/5. So for this sequence, you basically are looking for a pattern. And when you're dealing with the fractions, you kind of want to look for a pattern with the numerators and then a pattern with the denominators. Well, if you notice, the numerators are 1, 2, 3, 4, etc. And since 1/2 is my first term, right, this means that this would be n, then n plus 1, n plus 2, and so on. Whereas on the bottom, it starts at 2, then goes 3, 4, 5. So that means that my first term starts with n plus 1. So that means my formula would be n over n plus 1. All right, why don't you go ahead and try this one. Find a formula for this general term, a sub n, for the following sequence. And just in case you don't see them, they're kind of blended in. These are negatives right here. All right, let's see how we did. You should notice that the sequence is alternating signs. And if the sequence starts with a negative term, then the explicit formula must be multiplied by a -1 to the nth power. And if the sequence starts with a positive term, then the explicit formula must be multiplied by a -1 to the n minus 1 or a -1 to the n plus 1. So in this case, you should have gotten formula a sub n equals -1 to the n minus 1 times n plus 2 all over 5 to the nth power. All right, find a formula for the general term a sub n for the sequence 5, 1, 5, 1, 5, 1, and so on. Well, since this sequence is alternating between 5 and 1, then you find the average, which in this case is 3. We can now say that the sequence is alternating by adding 2 or -2 if we started at 3 each time. So then that means my general formula would be 3 plus -1 to the n minus 1 times 2. All right, so now we're going to look at convergent or divergent sequences. So a sequence, a sub n, has the limit L, and we can write that the limit as n approaches infinity of a sub n equals L, or as a sub n approaches L as n approaches infinity, if we can make the terms a sub n as close to L as we like by taking n sufficiently large, and if the limit as n approaches infinity of a sub n exists, we say that the sequence converges or is convergent. Otherwise, we say that the sequence diverges or is divergent. So basically, if the limit exists, you get a number for the limit, the sequence is convergent. If you get something undefined or one of the infinities, then we say that the sequence is divergent. So we're going to let a sub n be a sequence of real numbers. Then, if the limit as n approaches infinity of a sub n equals infinity, then we say that the sequence a sub n diverges to infinity. If the limit as n approaches infinity of a sub n equals -infinity, then we say that the sequence a sub n diverges to -infinity. And here is an example of the graph. And as you can see in this graph, as n gets infinitely large, the sequence values keep increasing infinitely. Now, if the limit as n approaches infinity of a sub n equals c, a finite real number, then a sub n converges to c. And so a graph of that type of sequence looks like this. And as you can see, as n gets infinitely large, the sequence is converging to a single number. And if the limit as n approaches infinity of a sub n oscillates between two fixed numbers, then a sub n diverges by oscillation. So something like this. So as you can see, the graph just keeps going in between, just kind of keeps going up and down. All right, so let's look at this example. A sub n equals cosine of 2 over n. So I want to take the limit of this sequence to determine if it converges or diverges. So when I put infinity in, 2 over infinity is just 0. So the cosine of 0 is 1. So therefore, this sequence converges. All right, so if we have this example, n over 1 plus the square root of n. So if I was to take the limit, and if I was to plug in infinity as is, I would get infinity over infinity. So this tells me I either have to do some algebra or go ahead and use L'Hopital. I went ahead and used L'Hopital. I can go ahead and simplify. So I get the limit as n approaches infinity of 2 times the square root of n. When I plug in infinity, I'm just going to get infinity out. So therefore, this sequence diverges. All right, so we also have a squeeze theorem for sequences. So the squeeze theorem for sequences says that if b sub n is between a sub n and c sub n, for n being greater than or equal to big N, for some big N, and the limits of a sub n and c sub n as n approaches infinity both equal L, then I can say that the limit of b sub n as n approaches infinity also equals L. Now there are some sequences that we can't take the limit of. These will primarily be true for those that alternate in signs. We will use the following theorem to help us with this. Now another theorem is if you were to take the limit as n approaches infinity of a sequence, the absolute value of a sequence, we would equal 0. Then we would say that the limit as n approaches infinity of the sequence equals 0. So basically, if you were to take the absolute value of it and you get 0, then we say the sequence also equals 0, so it converges. Now, the sequence r to the n converges if r is between -1 and 1, but not equal to -1, and diverges for all other values of r. Then we can say that the limit as n approaches infinity of the sequence r to the n power, if you get 0, you will get 0 if r, the ratio, is between -1 and 1, and you'll get 1 if the ratio equals 1. This theorem is useful for giving the convergence or divergence and value for when it's convergent of a sequence that arises on occasion. All right, so let's look at some examples. So for each example, we're going to determine if the sequence diverges or converges. All right, so let's look at the example a sub n equals cosine squared n all over 2 to the nth power. Since we know that the range of cosine squared n, we can apply the squeeze theorem. So I know that cosine squared n has to be between 0 and 1. And in order to make it look like my formula, I'm going to have to divide all 3 pieces by 2 to the nth power. And after simplifying, I get the following. Now, just like the normal squeeze theorem, I'm going to take the limit as n gets infinitely large for 0, and the limit as n gets infinitely large of 1 over 2 to the n. When I do that, I'm going to get that the limit of 0 is, of course, 0. The limit as n approaches infinity of 1 over 2 to the nth power will just give me 1 over infinity, which is 0. And so therefore I can say that the limit as n approaches infinity of this sequence equals 0. So therefore this sequence converges by the squeeze theorem. All right, now let's look at the sequence a sub n equals -1 to the nth power over n. Now, since this sequence is alternating signs, I'm going to go ahead and use that theorem that says if I can first prove that the absolute value of this sequence equals 0, then I can show that the limit also equals 0. So I'm going to take the absolute value of this sequence. When I do that, I'm going to just get 1 over n. And then when evaluating the limit, I'm going to get 0. So therefore, I can say that this sequence converges. And this theorem only works if the limit of the absolute value is 0. That's important. It has to be an absolute value of 0. All right. Now, if we were to take the sequence a sub n equals -1 to the nth power, And since it's alternating signs, I'm going to take the absolute value, which will just give me the limit as n approaches infinity of 1, which just gives me 1. Now, since the limit of the absolute value does not equal 0, we must take another approach. So that approach did not work. Now we have to start over. So if we notice, this sequence is in the form of r to the nth power, where r equals -1. All right, so if you remember the third theorem that we talked about a couple slides ago, it said that if r was between -1 and +1, but could not equal -1, the sequence would be convergent. For all other r values, it's divergent. Well, here the r equals -1, and according to that theorem, it can't equal -1 to be convergent. So therefore, this sequence diverges. All right, so now let's try this sequence. -1 to the nth power times n cubed all over n cubed plus 2n squared plus 1. So I'm going to start off by taking the absolute value of this, since I have an alternating sign. So now I'm going to evaluate the limit as n approaches infinity of n cubed all over n cubed plus 2n squared plus 1. If you were to just put in infinity now, you would get infinity over infinity. So you could either L'Hopital, or you can go ahead and factor out the n with the greatest power, which is n cubed, and cancel out the n cubes. And when you do either approach, you will get that the limit equals 1. Well, that doesn't work. So therefore, I have to try something else. So what is that something else? Well, if we were to look again at the absolute value of this sequence, you'll see that inside of that absolute value sequence, the sequence will either be -1 for odd terms or +1 for even terms. So this sequence is oscillating between -1 and 1. So therefore, the sequence diverges due to oscillation. All right, so now we're going to look at what are called bounded sequences. Given any sequence, a sub n, we have the following. First, we call the sequence increasing if a sub n is less than the next term, a sub n plus 1, for every n. We call the sequence decreasing if a sub n is greater than the next term, a sub n plus 1, for every n. And thirdly, if the sequence a sub n is a strictly increasing sequence or is a strictly decreasing sequence, we call it monotonic. For the fourth one, if there exists a number m such that m is less than or equal to a sub n for every n, we say the sequence is bounded below. The number m is called the lower bound for the sequence. If there exists a number big M, such that a sub n is less than or equal to big M for every n, we say the sequence is bounded above, where the number m is called an upper bound for the sequence. And then sixth, if the sequence is both bounded below and bounded above, we call the sequence just bounded. So keep in mind the following when we determine the previous 6 items. In order for a sequence to be increasing or decreasing, it must be increasing or decreasing for every n. In other words, a sequence that increases for 3 terms and then decreases for the rest is not a decreasing sequence. When finding the lower or upper bounds of a sequence, there is not just one number that works. There could also be a better bound. In other words, there are an infinite number of bounds for sequence. Some will be better than others. So a theorem that we have is that every bounded monotonic sequence is a convergent. All right, so let's look at some of these scenarios. All right, so for each of these graphs, I want to determine if it's an increasing or decreasing sequence, if it's monotonic or not, and if it's bounded above or below. So in this first sequence, you'll see that we are increasing because each previous term is smaller than the next term, and it's monotonic because it's strictly increasing. It doesn't go up and then down and then up and then down. And it's bounded below. As you can see, the sequence is bigger than this value, little m, and the sequence diverges. So as n gets infinitely big, you'll see that the sequence values keep increasing, so that's why it diverges. For this next graph, it's decreasing and monotonic and bounded above, and it diverges. This next one is increasing and monotonic, bounded above and below, and it converges. So this is the one I was talking about with that theorem. Notice that since it's strictly increasing, so monotonic, and it's bounded above and below, that means that the sequence has to converge to some value at some point. Now when we look at this next one, you'll see that it's oscillating, so it's not increasing or decreasing, and it's bounded both above and below. So even though it's bounded above and below, it is considered divergent since it's oscillating. It's not converging to one specific value. This next graph is decreasing and increasing, so it's kind of doing this kind of thing. It's not bounded, so therefore it diverges. All right, so let's look at some examples where you need to determine if the sequences are increasing, decreasing, or not monotonic, and if they are bounded. So if we first look at a sub n equals 2n minus 1. So the best way of determining this is to find the first few terms of the sequence. You may also want to graph it. So if I was to expand this sequence, I will get that the first term is 1, second term is 3, 5, 7, and so on. Since each term is larger than the previous term, we can say that a sub n is less than a sub n plus 1, which means that this sequence is strictly increasing and monotonic. Now, since this sequence will always be increasing, it cannot be bounded above. But the sequence does start at 1, which means it is bounded below 1. We just don't know exactly where. All right, so now let's say we look at a sub n equals 1 over n. If I was to expand this sequence out, I would get 1, 1/2, 1/3, and so on. Since each term is smaller than the previous term, we can say that a sub n is greater than a sub n plus 1, which means that this sequence is strictly decreasing and monotonic. And this sequence begins at 1 and decreases as it converges towards 0. This means that this sequence is bounded by being bound above by 1 and below by 0. So therefore, this sequence converges. All right, so let's look at this one. A sub n equals negative 1 to the nth power times 3 plus n. If I was to extend out this sequence, I would get negative 4, 5, negative 6, 7, negative 8, so on. Since this sequence is alternating between positive and negative, this sequence is not increasing or decreasing, so we say it is not monotonic. And the odd terms are increasing in the negative direction, and the even terms are increasing in the positive direction, which means that this sequence is not bounded. All right, this example, n plus 1 over n, if I was to extend out this sequence, I would get 2, 5 over 2, 10 over 3, 17 over 4, etc. Since each term is larger than the previous term, then we can say that a sub n is less than a sub n plus 1, which means that this sequence is strictly increasing and monotonic. And since this sequence will always be increasing, it is not bounded above, but the sequence does start at 2, which means it is bounded somewhere below by 2. Well, I hope you enjoyed learning about sequences, and I will see you in class tomorrow. Have a good night.